Hello and welcome to the pre-lab video for the Density and Measurement Lab. In this lab, we are going to be exploring density. We will be finding the density of two different nails. So we've got some large nails and some small nails. Both are some kind of metal. They are shiny and silver, but we don't know what type of metal they are. So we need to solve that mystery by determining the density. And of course, density is mass over volume. We will take the mass and volume of these nails in order to determine the density. And then we will be able to identify it based on the color and the density from this table of known densities of various metals. We're also going to be doing some calculations of error. So we've learned about significant figures, and that significant figures are a way to indicate uncertainty of our measurements. Now that uncertainty can come from the fact that our measuring devices are not perfect. In the case of this lab, we're going to be using some graduated cylinders from Amazon, plastic, and also some inexpensive jewelry scales, digital scales that also got from Amazon. So these devices are not precision lab grade devices. They probably are not perfect and do come with some error. Also, the error comes from us as humans reading these devices, measuring devices like a graduated cylinder. We have our own errors and biases. So the things that we care about when it comes to the certainty of our measurements. We want our measurements to be as accurate and precise as possible. A lot of times those words are used synonymously, but they are not synonyms. So accuracy is, think of it as like the correctness. How close is it to the actual density? And precision is sort of how repeatable your results are. So in this little funny figure here, this person, whoever threw the darts here, they were very precise. They always hit the same spot, but they were not accurate because they didn't hit the target. Versus this one here was pretty accurate because it always hit the target. It was pretty close, but they were all in different spots, so they were not very precise. So ideally, we want our measurements or our darts to fly both accurately and precisely. We don't want our measurements to look like this all over the place, neither accurate nor precise. So the way that we measure accuracy, how close our values are to the correct values, is using this measure of percent error, and the formula is here. And the way that we measure our precision, how close together our measurements are, is the standard deviation. So you'll be calculating both percent error and standard deviation from this experiment, the data that you're collecting. So in this experiment, we are going to be reading volumes from a graduated cylinder, and we need to make sure that we are reading those volumes correctly. So when we read volumes of liquid in a glass beaker or graduated cylinder, we want to read it from the bottom of the meniscus. Now in glassware, water does adhere a little bit to the glass and form this crescent-shaped meniscus. In our plasticware, it doesn't do that as much, so it will form a pretty straight surface and not too much of a meniscus, but still, the lowest point is where we're going to read that at, okay? We also need to make sure that we are reading to the correct sig figs. And this is a process known as interpolating. So we can read a certain place to certainty, but then the next decimal place over, we need to sort of guesstimate what the exact value is. So for example, in this image here, I would say that it is exactly at this marking here of 30. And since we know for sure that this marking is 30, and each of these markings here represents 1, I'm assuming these are milliliters, so we can read with some certainty every 1 milliliter, right? Because there are lines that mark those. So between those So between 30 and 30.1 is where we're going to interpolate. So we can interpolate one place past the ones digit. So we know pretty certainly, we can see with pretty good accuracy what the ones value is, and we are going to estimate one place past that. So you might say that this is 30.0 milliliters or 30.1 milliliters or 30.2 milliliters. Different people, different eyes might choose to read that slightly differently. Again, that contributes to the error and the uncertainty, but pretty much everyone we can say is going to say 30 point something. So we know that that 30 is a certain value, if that makes sense. All right, so when we are reading volumes, it's also important that we are reading from eye level, okay? So, and you don't actually want to pick up the tube here because then you might be slanting it. You can't never really be sure that you're holding it exactly straight. So what you want to do is you want to put it on a flat surface, and then you want to get down to eye level in order to read it correctly. Because if you're reading it from up here, you're reading it at an angle and your line of sight is not necessarily going to be lined up to the correct marker. So always read at eye level, always read at the bottom of the meniscus, and always interpolate one place past, one digit past the smallest marking. So these markings are in the ones place, so we would interpolate to the tenths place. All right, so there's some practice problems here for you to solve. Practice reading these two graduated cylinders. And in this problem, you are also going to be determining the volume of this little cylindrical piece of metal here. The volume, of course, will be the difference between the volumes of water because this metal piece will displace the same amount of volume as itself. Alrighty. The other piece of equipment that you're going to be using is a digital scale. Let's see if I can lower this down here. All right, so the digital scale, it uses AAA batteries, so you might need AAA batteries, but you can also always use the charging cord and plug that in. It won't hold a charge, so it has to be plugged in order to use it. All right, so first things first, you got to open the plastic cap here. It's not going to work. If you don't, sometimes it falls off. That's fine. You want to make sure that your scale is clean and doesn't have bits of chemicals on it. Mine does, and I don't have a paper towel handy, so I'm just wiping it with my hands. Not the best policy, but alrighty, we fast forwarded a little. Oops! I don't know what that means. Okay, so we have our scale on a stable surface, and now I'm going to try to angle the camera so you can see the readout. All right, so the first thing we need to do is calibrate the scale. So we're going to turn it on, and it says hello, and then it goes to 0. And we are going to press and hold the M key until it tells us what weight we want to calibrate with. Most of the scales are 100 grams, but some are 50 grams. So it says 100 grams, so I have my 100 gram calibration weight. I'm going to click the M where it says cal, and it's going to blink and flash 100 and then pass. It is now calibrated now that it is back to saying 100 and not flashing. So now our scale is ready to use. We take that off and it's back to 0. All right, so that is an important step. Now, the reviews online said that when you tear the scale, which means you put something on it and you return it to 0, so for example, if we put this whole thing of nails on here, all right, it's 31 point, I can't read upside down. All right, now let's do this. Let's do something empty. Whatever, let's do the lid here, okay? This lid, let's pretend we're using this lid as like a cup to measure something out, and it is 19.372, and we want to weigh out 10 grams of water, okay? It's easier to do that if we tear this, which means it goes to 0. It's not so steady, maybe I'm breathing on it, all right, and then we can add our water, for example, until we get up to the 10 grams or whatever that we want. And that way it's easier to see the weight of the thing we're measuring, the water, rather, and we're negating the weight of the measuring vessel. So I do have you guys going through some steps to practice tairing and measuring and seeing if that actually affects the accuracy of the measurements and precisions of the measurements, to see whether we actually want to use the tair function in lab or not. So I'll tair it. Tairing is also called re-zeroing. Alrighty, so I'm back on camera. So your job, there's very few procedural steps here because you are going to be kind of working this out yourselves. The things that you need to consider before you actually start this experiment are how many nails you want to use. I will tell you, one nail is probably not going to give you great results because it's not going to result in enough displacement for you to be able to read it very accurately or precisely, but definitely not accurately because it'll be so small. So definitely use more than one. Don't use all of them because you don't want to use more than can fit, right? If you need to be able to displace the water, you can't use more larger volume of nails than water. So you need to use somewhere in between 1 and a number that will be too large of a volume. Remember, when you're doing water displacement, everything needs to be under and submerged under the water in order to read that new volume. If you have any of them sticking out, then you're not getting an accurate reading. So then you also have to decide what volume of water you're going to use. Again, you have to be methodical in this because you don't want it to go above the 10 milliliter marker, and you want to be able to read it. And then lastly, you need to figure out which place you're going to be able to interpolate to. And it's not terribly accurate on these cheapo little plastic graduated cylinders. So you'll record your data here. Do record how many large nails and how many small nails you chose to use. It doesn't matter if different people use different numbers, okay? The density, remember, is an intrinsic property, so no matter how many nails you use, the density measurements should come out the same. So your mass and volume measurements will be different, but your density measurements should come out roughly the same. With error being more in your technique than in the actual differences between the names. So you'll calculate your density from your mass and volume, and then you're going to go around the class. Since I have you guys working in pairs, I just called you all teams, and you will record the density of all the other teams, including your own team, for each of the nails, and then you'll calculate an average. So essentially, you can think of it as each of these teams is responsible for doing a separate trial. You're each doing one trial for a total of 6 trials. In science, it's very important. Repetition and getting the same results, repeatable results. If you do an experiment once and you get results, it means next to nothing if those results are not repeatable. This is also a great way for y'all to check your work. If one group is an outlier and has some really messed up data, they probably made a mistake somewhere in their calculation. So this is a good way for y'all to peer check yourselves and your work and be able to redo it if you did it incorrectly the first time. And so from these averages, you'll be able to do some of those statistics. You can, well, first of all, from those averages, you'll be able to determine what the identity of the metal is by comparing it to that table on page 1. And you'll be able to check the accuracy of the class results by calculating the percent error and the precision by calculating the standard deviation. So I do have some space here for you to show some of your work. I just want to see that you know how to do it, even if you don't show every single calculation. And also, whenever I have a short answer question, a one-word response is not going to cut it. I pretty much always ask you to explain, and if I don't ask you to explain, I probably still want you to. So that is the Density and Measurement Lab. Have fun.